Hi, I'm Alex Craig, and my thesis proposal is hydrogen peroxide vapor decontamination of polylactic acid fibers. Since 2002, there have been multiple pandemics. In 2002, there's SARS, and this outbreak worldwide, 8,098 people became sick, with 774 people dying from the disease. In 2009, H1N1, or swine flu, was a very big outbreak here in the US and Mexico area. And in the US alone, the CDC estimated there was 60.8 million cases, and there was 2,469 deaths that occurred with them. In 2012, the Middle East Respiratory Syndrome, or MERS, outbreak occurred, and there was 2,519 cases with 866 deaths worldwide. And in 2014, an Ebola outbreak occurred, and there was 28,652 cases, and there was 11,325 deaths worldwide. And obviously these pandemics are becoming a lot more frequent. There was 7 years between SARS and H1N1, 3 between H1 and MERS, and then 2 between MERS and Ebola. And currently we are in a pandemic. COVID-19 has changed the world completely. In the US alone, 15.5 million people have caught COVID. That is approximately about 5% of the US population. And out of that 15.5 million people, 290,000 people have died. And these pandemics have shown that there's a great desire and need for reliable methods to keep areas clean. So currently, a widely used decontaminant is hydrogen peroxide vapor, and it's widely used to decontaminate hospital rooms, laboratories, and medical equipment. And seen here on the slides are two of the main company devices that actually make hydrogen peroxide vapor systems. And on the left, there is Bioquell, who calls their process hydrogen peroxide vapor. And on the right is Thesis, who calls their process vaporized hydrogen peroxide. There's a few differences between the two. And one of the differences is that Thesis actually doesn't start their decontamination process with dehumidification. And I'll explain a little bit more what that is in the next slide. But the way they do it, they rely on the formation of microcondensation on the surfaces of the space they are in. And Thesis also has a higher concentration that they produce, so they get up to about 600 to 800 ppm, while the Bioquell one normally only does 200 to 300 ppm. And because of this, that higher concentration, Thesis has a longer decontamination time. They normally have about an 8-hour cycle, while Bioquell is normally like an hour and a half to 2.5 hours. However, this common factor is that they both use 35% hydrogen peroxide to complete their process. So this is a typical hydrogen peroxide vapor decontamination cycle. And as you can see, it consists of 4 main phases, and this includes the dehumidification stage, which is seen right here, the conditioning phase, which is the second phase, then you have the decontamination itself, and then the last phase is the aeration phase. So during this first phase, this is when the relative humidity is normally reduced to approximately 30 to 40%. And as I said before, Thesis doesn't do this phase. They skip straight into the conditioning phase. And in this phase, this is when the decontaminant is produced through the process of vaporization to achieve the desired concentration that they want in the enclosure. And then the next stage is the decontamination time, or decontamination. So this is when they continuously introduce hydrogen peroxide vapor to keep the target concentration, and then they carry it out for their desired exposure time, whenever that is 2 hours or 4 hours. And then the last phase is the aeration phase. And during this phase, the hydrogen peroxide is no longer introduced, and the residual vapor that's left over is safely decomposed into water and oxygen. Sometimes it's recirculated for a chemical destroyer to help speed up this process, and this is continued until the vapor concentrations are at a safe level. So on this slide, these are two of the studies that have been done. So there's actually been many studies on how hydrogen peroxide vapor affects certain materials and its efficiency against bacteria, viruses, and fungi. So the picture on the left is an example of a plane going through decontamination. And these giant 18-wheelers on the side are actually the decontamination units. And in this study, for this picture, they actually tested how the metals in the plane were affected by hydrogen peroxide vapor. And they found that the microstructure effects were relatively small, no matter how long how many times they did the decontamination cycle. And then they also found that there was no systematic effect on the tensile properties of the post-exposure corrosion resistant. And they also, in a different study, but using a plane also, they evaluate the polymetric textile materials that are in there. And this was a key study because many polymetric materials are susceptible to absorption of moisture. And it was seen that these materials that were tested actually had an increase in weight due to the absorption of hydrogen peroxide and a decrease in the tensile strength. And then on the right here is a classic DEF kinetic curve, which is basically a trend that the DEF of microorganisms follow when they're being exposed to stuff. And hydrogen peroxide vapor actually follows this DEF curve and achieves this against viruses, bacteria, and fungi. So going into the material that we're used for this process, polylactic acid, or PLA, is a widely used thermoplastic polymer, and the molecular structure can be seen here on the left. And this polymer actually has excellent properties such as biodegradability and biocompatibility, and it also has high tensile strength and elastic modulus. And it's been used in a variety of ways. It's been used in 3D printing, which is what this spool here is on the right for. And then it can also be used in biodegradable medical devices such as wound dressings. So what are wound dressings really used for? So they're a very common solution for helping chronic wounds heal. And they actually allow for the exchange of gases while maintaining the appropriate humidity throughout the wound. And they also are very impermeable to bacteria and water, helping keep the wound clean and dry. And they can also be drug-loaded to help speed up the healing process. So wound dressing fibers are typically produced through the process of electrospinning. And during this process, there is a potential risk of contamination. So wound dressing fibers can be decontaminated to help decrease the potential risk of infections. So our research questions for this project were to how to generate hydrogen peroxide vapor and how to measure the hydrogen peroxide vapor concentration being produced. And then the second question was, are drug-loaded PLA fibers compatible with hydrogen peroxide vapor at various decontamination times? So the main objectives for achieving both of these research questions were, the first one was to determine the hydrogen peroxide vapor concentration being produced. The second objective was to perform hydrogen peroxide vapor decontamination of PLA samples. And the third objective was to determine the sample characteristics of the PLA fibers after they've been through the various decontamination times. And then the fourth objective, which I haven't started yet, is to complete and determine the quantitative effects of hydrogen peroxide on drug-loaded fibers. So before we could determine the hydrogen peroxide vapor concentration, we would need to design a device that would actually produce the hydrogen peroxide vapor. So after researching how the bigger companies actually produce the hydrogen peroxide vapor, we decided to use a modified bubble machine. So there's a couple of reasons we went with the bubble machine. First, it had a powerful enough fan to produce the vapor after blowing through a wick. Second, it was extremely portable and it could run off of batteries. So if needed to, we could just use the batteries, but it also had a plug in case we did want to just plug it in and not use the batteries. And then second, the well was large enough to store hydrogen peroxide without it getting into the electronics or causing issues. So the original bubble machine is here on the left. And the first modification we made was to remove this spinning wand that is used to blow the bubbles out. And then the second modification we did, we cut up a wick and inserted it into the well and then wrapped it over so be in front of the fan. So when the hydrogen peroxide was absorbed up the wick, it would be blown out by the fan. So this was the first test set of runs we did to test to see if the device would actually produce vapor. So first we tested how much humidity was being produced by the device itself. So a humidity sensor was placed at 5 and 26 centimeters away from the front of the bubble machine for 20 minutes. So the reason why it's actually 26 and not 25 is that during these experiments, we were also testing a second design to see if that one would be a better option to use. And the way the second design was, we weren't able to actually get it to be 25. It could only get to 20. We were only able to get it for 26 because of the angle it was being measured at. So to keep the uniformity for comparison throughout the experiments, we just made the bubble machine 126 also. And we tested the humidity levels at 3.5, 5%, and 30% weight per weight hydrogen peroxide. So the second setup we did, we tested the concentration being emitted by the device, and we placed the hydrogen peroxide sensor, we placed it at 5, 10, 15, 20, and 26 centimeters away. And again, we used 3.5%, 5%, and 30% weight per weight liquid hydrogen peroxide. And we kept the nozzle of the sensor at the same level to keep the accuracy throughout the experiment, so we could measure how much hydrogen peroxide was being produced at that, straight out from the bubble machine. So the next setup we did was a box experiment. We wanted to see how well it would actually produce hydrogen peroxide vapor in an enclosed space. So we actually used a cardboard box, and then we cut a hole out inside, cut a hole out in the middle, and then we placed the device and the humidity sensor inside the box, and then we sealed the box with plastic wrap, and we taped up the edges to try and create like a full seal. And then we poked the nozzle of the hydrogen peroxide sensor through the plastic wrap, and then sealed the hole the best we could with tape. And then we took measurements over a 120-minute time period. So this next one is the last setup we used was the glove box, and this was to determine the concentration and humidity in a controlled environment. And this environment was also the one that we were going to perform the decontamination of the PLA fibers. So first, the PLA fibers would be placed into Ziploc bags and placed inside the glove box. And then the humidity sensor and the bubble machine were placed also there. So that you can see the bubble machine here, and the PLA samples would be back here in the Ziploc bags. And the sensor is like approximately here in the back. And then after everything was inside, we would seal the entrance, so we would just put the lid on. And then next, we attached a hose to the back of one of the valves that are in the back. And then we attached the sensor nozzle to the hose so it would be able to read the concentration inside the device. And then we would turn on the bubble machine and let it run. And then once the concentration and humidity had stabilized throughout at the levels we wanted it, we would remove the samples from the Ziploc bags and then place them still at the furthest point away from the device. And then we perform the decontamination of times of 1, 3, and 5 hours. So to actually make the PLA fibers, we performed electrospinning. So the way electrospinning works is that they charge the polymer particles in a strong electric field. So this electric field is created by this power source. So the positive side is attached to the metal needle tip, and then the negative is connected to the collector plate. And inside the syringe, that's where the polymer solution will be. So once it's turned on, the electric field pushes apart the particles and actually creates a whipping effect. And this is how the fiber is formed and collected on the collector plate. And the fiber solution was 15% PLA weight per volume, 15% aspirin weight per weight. And a voltage of 8 kilovolts was applied with a flow rate of 10 microliters per minute. And then the collector plate from the tip of the syringe to the plate was 10 centimeters. So now we're going to discuss the hydrogen peroxide calibration runs results. So this is the humidity in the fume hood at 5 centimeters. And as you can see, the 3.5 and 30% have a slight increase over the 20-minute time period. And as you can see, the 10% is starts off a lot higher. And we believe this was because it was done right after the 3.5% experiment, so that the relative humidity inside the fume hood was higher when it started. And we actually ran the 30% one the day after, which is why it's at the same level as the 3.5, because it would be in the same starting environment. And then this is the relative humidity in the fume hood at 26 centimeters. And you can see about the 3.5, 10, and 30% will have about the same increase over the 20-minute period. And again, we believe the 10% is higher than 30 in the 3.5 because it was completed right after the 3.5 experimental run. And these two graphs basically show that the device was actually capable of producing a vapor and it was actually being able to be seen. So the next one we did was we measured the concentration in the fume hood. And as you can see, the 3.5, it stays at 0% throughout the experiment. And we believe there just wasn't enough hydrogen peroxide in the air for the sensor to register the concentration. And then the next one is the 10%, and you can see it slightly increases over the time. Then it reaches about 15 centimeters, and then it starts decreasing. And then lastly, we have the 30% hydrogen peroxide. And as you can see, it starts off higher and then drops as the experiment goes on. And we believe that was due to the hydrogen peroxide actually being heavier, and so it was dropping as the distance increased. So the sensor wasn't able to read it as it was kept at the same level throughout the experiment. So this is our box experiments results. And as you can see, the hydrogen peroxide concentration and relative humidity, they quickly increase in the first 20 minutes or so, and then they slowly start leveling out as the time continues. So the relative humidity was about between 70 and 80%, and the hydrogen peroxide concentration was approximately between 100 and 110 ppm. And we knew this wouldn't be exactly what we would see in the glove box experiment, as you'll see in the next slide. We think it was lower because the cardboard was actually absorbing some of the hydrogen peroxide concentration, so it was actually decreasing the amount in the box. And so this run is the glove box experiment that we did. And this data is extremely important as it gave us the parameters of what the hydrogen peroxide concentration and the relative humidity should be about when we're performing the decontamination on the PLA fibers. So as you can see, there's a rapid increase for the first 30 minutes, very similar to the box experiment, except these numbers are a whole lot higher than what the box experiment reached up to. And then you can see this concentration relative humidity start leveling out as the experiment goes on for longer. So the relative humidity was between about 80% and 90%, and the hydrogen peroxide concentration was between 180 and 200 ppm. So now we're going to talk about the results from the testing of the PLA samples after they went through decontamination. So this is the percent weight change of the PLA. So to calculate this, samples were actually cut into 1/2-inch diameter circles, and then they were weighed before, and then they were placed inside the glove box and decontaminated for 1, 3, and 5 hours, and then the weight was taken afterwards. And as you can see, there was a very slight increase of weight for the 1 hour, and it was approximately 0.79 plus or minus 4.42%. And then for the 3 and 5 hour, you can see there's a decrease of negative 3.87 plus or minus 10.56 for the 3 hour, and a negative 4.96 plus or minus 9.11 respectively for the 5 hour. And since there's no significant increase in weight, this shows that the PLA fibers were not actually absorbing the hydrogen peroxide vapor. But as you can see, there was a decrease, and this probably means that the hydrogen peroxide is degrading the fiber as the decontamination time increases. Okay, so this is the percent area change, and the same process was followed. The samples were cut into the 1/2-inch diameter circles, and then the area was measured before and after, the area was measured before decontamination, then they were decontaminated for their 1, 3, and 5 hours, and then the area was measured afterwards. So the percent area is relatively small. For the 1 hour, it was about 0.4%, plus or minus 1.05. For the 3 hours, a little bit more, it was 2.17 plus or minus 3.4. And then for the 5 hours, negative 1.2 plus or minus 1.16. And the fibers had a very minimal area change, which showed that they weren't being deformed by the hydrogen peroxide vapor as the decontamination time increased. So this is the fiber microstructure of the PLA. So picture A is the PLA after 1 hour of decontamination. B is after 3 hours, and C is after 5 hours. And as you can see, as the decontamination time increased, the fiber microstructure didn't show any changes, and there's no visible changes in the drug crystallization as the time increased. And this is extremely important as the crystallization of the drug makes the drug delivery system unstable, which can actually cause a decrease in the drug loading efficiency and make the release behavior very unpredictable, which is not good for when you want to release a certain amount of drug in a time frame. So this graph here is a representative concentration and humidity for all the experiments that were performed throughout the PLA fibers that were tested for their mechanical properties. So you can see the hydrogen peroxide concentration held fairly steady throughout the experiment. It was between 190 and 200 ppm. And then the relative humidity was between 80 and 90%. And this was what we saw also in the glove box experiment. So this is what values we were looking for when so we could start the decontamination time and make sure that the levels stay throughout there. If they started to drop, we knew something was wrong. Either the device was running out of power or there was just not enough hydrogen peroxide in the well. So this is a stress strain graph of the PLA samples. So to obtain this, the PLA samples were actually cut into dog bone shapes, and then they were decontaminated for the 1, 3, and 5 hours. And after decontamination, the samples were placed into an Instron mechanical tester, and then the stress strain data was acquired. And from this stress strain data, you can see find the Young's modulus, which is the slope right here on the beginning of the graph. And then you can find the ultimate tensile strength, which is the maximum point of the graph itself. And then you can also find the elongation to failure, which is when the sample actually breaks in half, which you can see here. So one of the most important things you can see in this graph is actually this necking behavior that is occurring in the one control. So basically in this beginning region, the amorphous structure that is between the semi-crystalline structure is unfolding. And then once it's all unfolded, there is a sudden drop because this is when the semi-crystalline structure starts to be unfolded throughout the experiment. And as you can see, there's quite a sharp necking in the control, and it's still visible in the 1 hour, it's just not as drastic. And then as you move on to the 3 and 5 hour, you can see there's no necking that is occurring. So this decrease in necking is actually due to the plasticizing effect being increased that occurs after the hydrogen peroxide decontamination. And we believe that this indicates there's a potential replacement of the hydrogen bonds with hydrogen peroxide in the molecular chain. So this is the elastic modulus and the tensile strength data that we got for from the stress strain graph. And it can be seen that both of them have decreased with an increase of decontamination time. So for the control, the elastic modulus was 138.6 plus or minus 0.1 megapascals. And then it decreases to 119.3 plus or minus 0.3 megapascals. And then it goes to 65.5 plus or minus 17.3. And then it decreases some more to, or it keeps going till 73.73 for the 5 hour. And since the elastic modulus also decreases, it suggests that there's also an increase in the plasticizing effect. And then you also have a decrease in the tensile strength. So the control was about 4.9 plus or minus 2 megapascals. And then it drops to 3.8 plus or minus 2.4 for the 1 hour. And then for the 3 hour, it is 3.6 plus or minus 0.9 megapascals. And then for the 5 hour, it increases ever so slightly to 4.2 plus or minus 0.4 megapascals. And since the control has the highest tensile strength, this suggests that the semi-crystalline molecular structure is actually being plasticized throughout the decontamination process. So lastly is the elongation to failure. So you can see there's a decrease between the control and the 1, 3, and 5 hours, but between the 1, 3, and 5, it's relatively unchanged between the times. So the original decrease from the control to the 1 hour indicates that the PLA fibers are actually becoming more brittle after they're being exposed to the hydrogen peroxide vapor. But however, the increase of exposure time has very minimal effect on the elongation to failure. So our preliminary conclusions for the initial research is that there's minimal changes in the dimension and weight after various cycles of decontamination. There was less than a 5% decrease in the weight, indicating that the PLA fibers were being slightly degraded, and there was also an increase of 3% in the dimensional change, but that wasn't very significant. And from the naked eye, there was no obvious signs of deformation or any degrading happening. From the fiber microstructure, we were able to see that there was no drug crystallization occurring as the decontamination time increased. And then lastly, there was a decrease in the stiffness as the decontamination time increased due to an increase in the plasticizing effect. So for our future work, we actually have two hypotheses that we're looking at. So the first hypothesis is that the intermolecular bonds between the drug and the polymer are actually being replaced by the hydrogen peroxide. And to determine if this is true, we'll actually be performing an in vitro drug release. And this drug release will occur at 1, 2, 4, 8, 24, and 48 hours. And then we'll actually compare it to a cumulative release of the drug that has just the original sample. And then we'll know if the drug release is faster. We actually know that the intermolecular bonds between the drug and the polymer are actually being replaced. And this release would be faster because the drug is now sort of free floating inside the polymer. And if it's the same or very similar, that will actually lead us to more towards hypothesis 2. So if hypothesis 2 is occurring, we believe that the plasticizing effect is only really occurring within the PLA matrix itself. So to test this hypothesis, we'll actually produce a blank PLA sample. We'll then perform the decontamination times of 1, 3, and 5 hours. And then we'll actually perform mechanical testing on this. And if we're able to see a decrease in the stiffness after decontamination, we know that there's something that's happening with the intermolecular bonds. And then we'll also perform Fourier's transfer infrared spectroscopy, or FTIR. And this will allow us to see if there's any change of the peaks, which means that the bonds within the molecule are actually being changed. And then lastly, we'll perform differential scanning calorimetry. And this will allow us to see if the glass transition temperature and the melting temperature have actually changed in comparison to the original. And this also will let us see if there's a change in the intermolecular bonds, because when those bonds break, it'll probably decrease the glass transition and melting temperature. So this is a picture of the incubator that will actually be forming the drug release in. So PLA samples of 7/16 inch disc will actually be decontaminated for the 1, 3, and 5 hours. And then they'll be placed into a glass vial, which actually contains phosphate buffer saline medium. And they'll be incubated at 37 degrees Celsius. And then liquid samples will be taken at the specified time points. And then this data will actually be compared to the original drug release graph. So this is actually the original drug release graph. And for hypothesis 1, if it is true, we're expecting to see a faster drug release here. So it'll probably be a higher rate in this section here, and probably would level out more, be higher overall. And then if hypothesis 2 is more correct, we expect it to be very similar to the one shown. And we might end up having something in between. It might have a faster drug release, but also very similar in the end section. And this means that both of them are actually occurring at the same time. And we should be able to see which one is occurring more throughout the process. So I'd just like to thank Dr. Brown and Dr. Fumo for their advice and support throughout this process. I'd also like to thank Dr. Cho for his guidance and continuous support, patience, and encouragement throughout this thesis proposal and throughout doing research with him. And I would also like to thank Addison and Aaron and other biomaterial lab members for their continuous support and encouragement throughout. Any questions?